Bismillahirrahmanirrahim. Welcome to this problem session. In this problem session, I'm going to solve the final exam of the previous semester, term 211. Let's start with the first problem, in which we want to do some number, basically, number conversion, but for signed numbers. Okay, so so first of all, we have this number here, minus 27. Minus 27, we'd like to represent it in 6-bit sign and magnitude, and 6-bit 1's complement, and 6-bit 2's complement. Okay, so first of all, we need to find out what is plus 27. Plus 27 is nothing but plus 31 minus, which is basically 5 1's, okay, minus in binary, minus 4, okay? So therefore, plus 27 is going to be 0 for the sign, and then followed by 5 1's, and then minus of course, 4, which is 1 0 0. So this one here is going to remove this one. So the answer is going to be 0 1 1 0 1 1. Okay, so this is plus 27. So in sign and magnitude, what is minus 27? Basically, we replace this bit with a 1. Okay, so it's 1 1 1 0 1. Okay. Excuse me. Now in 1's complement, what you need to do is to have the plus 27, which is basically 0 1 1 and then 0 1 1. All right. And in 1's complement, what you need to do is to complement all the bits. So the 1's complement solution is 1 0 0 1 0 0. And in 2's complement is 1's complement plus 1. So we just add 1 to this number here, okay? So it's 1 0 0 1 0 1, right? Okay, next question. Given that A is this number here, binary number, and this B is this binary number, are 8-bit signed integers in 2's complement representation, then the decimal value of A, okay, we know that the bit number 8 is the sign bit. So its magnitude is going to be minus 128, which is minus 2 to the 7, right? Minus 2 to the 7 plus 2 to the 6 plus 2 to the 5, okay? And then 2 to the 4 is 1 2 3. Yeah, 4 is missing, and then 3 is there, and then 2 is there. Okay, 1 and 0 are the powers are missing, and if you calculate this, you'll find out it is minus 20. Okay, in decimal. So A has a value in decimal, which is negative 20. All right. Okay. Okay. The next question is that the 8-bit sum of A plus B. Okay, so we need to just add A and B and see what is the result. So I have A, which is 1 1 1 0 1 1 0 0, and then B is 1 1 0 1, and then 0 1 0 1 1 0. Okay, add these together. 0 1 with a carry 0 with a carry 1 0 with a carry 1 0 with a carry 1 0 with a carry 1, and then 1 with a carry 1, and then 1 with a carry of 1. Okay, so this is the final carry of this card. Since the last two carries are the same, there is no overflow. Okay, no overflow. So since this carry and this carry are the same, there is no overflow, and this is the answer. Okay, so a plus b is 1 1 0 0 0 0 1 0. Okay, produces no overflow. Okay, no overflow since over the two carriers are the same. Right, what about this problem here? Okay, given a clock with a cycle period, okay, of 0.2 nanoseconds, then the frequency is 1 over 0.2 nano, okay, second, so it should be hertz. 1 over second is a hertz, okay? And if you calculate this, it will be 5 gigahertz, okay? All right, and given a clock with a frequency of 4 kilohertz, then the cycle is 1 over that, so 1 over 4k into second, okay? 1 over hertz is a second, okay? If you calculate that, it will be 0.25, quarter of a millisecond. Okay. So next question is a very long question. Okay. We are given a very long code. Okay, and we are requested to answer or fill in some blanks. The type of reset. Okay, let's check the reset. So reset is going to be, first of all, since we are not checking for reset in the sensitivity list here in the always block, then reset is going to be synchronized with the clock. So synchronous reset is synchronous, and since we are checking for reset itself, this is if reset equals 1. This one is if reset equals 1, so it is an active high. Okay, active high signal. So it is, first of all, it's synchronous and it is active high. Okay, all right. The second question is if S is 0 0, okay, 2-bit of being 0 0, function is 0 0, so 0 0 is not mentioned here. Okay, so it means that I am not going to change Q. So this is a no change. No change. Okay. And if it is 1 0, then we are basically shifting to the left with a serial input. Okay. So it's a left operation, is a left shift with serial input SI. Okay. And the final one is 1 1, function 1 1. Okay, you can see that we are given, for example, so this is Qn minus 1, and then Qn minus 2, all the way to Q0, right? And then this becomes after the change, we take this and put it in here, okay? And the rest is going to be the same. So Qn minus 1 all the way to Q1, all right? So it's like this is a rotate operation, okay? So it's a rotate rotate to the right operation, okay? Rotating to the right. This is the direction of the rotation here. Okay, rotate right. Operation is rotate right. All right. Okay. All right. So this is the question 2. Okay. Design a combinational circuit that computes y equals x squared minus x. Okay, where input x is the input x and y are both signed binary numbers in 2's complement representation. X is 3-bit X is 3-bit, all right? What is the minimum number of, what is the minimum number of bits? So this is the question now. What is the minimum number of bits needed for the signed output Y, okay, such that an overflow does not occur at all? Okay? First of all, you need to find the maximum and minimum Y, okay? Since X is signed, okay, so we have to find out the minimum and maximum, all right? So the minimum of Y is going to be, first of all, the minimum of X squared minus the maximum of X, okay? Because we would like to minimize this expression because there is a minus sign here. We take the maximum of X, okay? So, right. So since X is a 3-bit number, it ranges from -4 all the way to +3, okay? And X squared, the maximum of X squared happens when X is -4, okay? Because the answer is going to be, since X squared is always positive, its minimum is when X is 0, okay? When X is 0. So this is equal to 0, and then minus the maximum of Y. The maximum of Y is -3, so it is +3. So the minimum of X is +3, and the maximum of X is going to be, of Y, I'm sorry, is going to be the maximum of X squared minus the minimum of X, okay? And that equals the maximum of X squared is going to be -4 squared, which is 16, right? And then minus the minimum of X, which is -4. So it will be +4. So this is going to be +20. Okay, so we have a range of Y, okay, being from +3 to +20. So Y is always positive. Okay, Y is always positive. But since in the question it says that they are both signed, okay, then we add the sign bit to Y, okay, add the sign bit to Y. So basically, Y is going to be, if it is unsigned, then we have to be able to encode 20, okay, which requires 5 bits, okay. And in addition to the sign bit, it will be 6-bit. So Y is 6-bit. Okay. So here, the table, in the truth table, okay, we have what? We have Y5, which is the sign bit, okay, which is always going to be a 0 because Y is always positive, okay. And we have Y4, Y3, Y2, Y1, and Y0, okay. So when X is 0, we have 0 minus 0, the answer is 0. 0 squared minus 0, the answer is 0. And when X is 1, 1 squared minus 1 is 0 also. Okay, and when X is 2, okay, we have 4, 2 squared minus 2, okay, 4 minus 2, which is 2. Okay, so we have a +2 here, +2. And then when it is 3, it is X is +3. We have what? We have 9 minus 3, which is +6, right? +6. All right. And then we have a negative number here, okay, which is -4. So this is a -4. minus 3, minus 2, and then minus 1. All right. So minus 4 squared is 16, right? And then minus 4 is going to be plus 20. Okay. So plus 20 is nothing but 1, 0, 1, 0, 0, because 20 is 16 plus 4. Okay. Plus 4. All right. Okay. For minus 3, it is what? It is 9 plus 3, which is 12. Okay. 0, 1, 1, 0, 0. All right. And then minus 2 is going to be 4 plus 2, which is 6. Okay. Or plus 6. And then finally, minus 1 is going to be minus 1 and minus 1. So minus 1 squared is 1. Minus 1 is going to be plus 1. So the answer is going to be 2. So this is 0, 0, 0, 1, 0. And that's the truth table. Okay. That's the truth table. Okay. This concludes this question. Let me stop here. Okay, the rest of the question is is in another subject. So let me stop here to make the video a little bit shorter. Okay, and then continue in another video.